Yes, hi everyone, thanks for coming. Thank you for the wonderful meeting. I'm glad to be back at the CCA. So I was asked to talk about how we do seeding in cosmological simulation for galaxy formation. So going from zoom in all the way to the very large simulation, such as the one in the background here. Of course, the field of black hole formation have been driven by science, and I'm not going to talk at all about science, but we all know that this has been really, pushing the field. I'm currently working at the Max Planck Institute. I'm moving to Geneva, and I'm hiring a postdoc and a PhD student. So if you're interested, buy chocolate and also simulation, please join us in Geneva. So I like to start with kind of the basics. This is showing redshift as a function of the mass of massive black holes, and all the detection that we had prior James Webb were basically below this line here. So in the local universe, we have this great diversity of massive black holes, from the least massive one in dwarf galaxies all the way to the biggest one in the largest elliptical. And as we go to higher redshift, of course, we only see the active black holes, all the way to the high redshift quasars, redshift 6, 7, so really less than 1 gigayear after the Big Bang. And those guys have been great to tell us that at least some of the black holes must have formed very early on in the history of the universe, so that they had time to accrete even more gas and produce this population of extreme objects very early on. So James Webb has been pushing what, our observational limit, what we're able to observe. So now we have interesting, sometimes puzzling discovery of AGN, or what seems to be AGN at high redshift. So we're getting close to really where we think the massive black holes are forming. We'll have other telescopes that will help us to constrain the formation of black holes. So Euclid, but also telescope in X-ray. So for example, Athena, Axis, and I encourage everyone to look at the paper that were released on Axis recently, maybe links. We also have local search for low mass black holes in dwarf galaxies, and this is also providing us with nice constraint on the formation of massive black holes. And of course, in 10 years from now, or about 10 years, we'll have LISA, which will be able to detect all the merging black holes with mass between 10 to the 4, 10 to the 4. So 10 to the 4, 10 to the 7 solar mass. So, the field is progressing, and we need to improve our subgrid physics for massive black hole formation. So of course, at the moment, the constraints are still poor. So there are many theoretical mechanisms that can explain theoretically the formation of those massive black holes. So I'm going to go through some of the mechanisms without explaining them too much, because it will be too long. But if we look at the timeline of the universe history, we think that black holes can form either before even the first galaxy, so very, very early on, possibly as early as inflation, and then most of the common mechanisms in the field are actually forming black holes within galaxy formation, or at least at the time where the first galaxy starts forming. So please do not ask me any question on primordial black holes, either how you can form black holes from the collapse of cosmic string loops, expertise. But we wrote a review recently that you can check out. I didn't write the part on this, obviously, but please have a look. And then we have mechanisms that form black holes within a galaxy formation context, and then those are the ones that we eventually want to model in cosmological simulation. So the idea for most of those mechanisms is to form black holes out of the collapse of a massive star, massive stellar-like object at high redshift. And the mass of those massive stars is set by the Jeans mass. So it's proportional to temperature of the gas. So the content of the medium is very important for what type of object we can form. So first, in metal-free environment, very high redshift, we think that black holes can form in mini halos from the remnants of the first pop twisters. Of course, we don't know the IMF, the initial mass function of those pop twisters, but between 10 and 1,000 seems reasonable, and you can form black holes of about 100 solar mass, maybe. And then in atomic cooling halo, if you do not have efficient coolant, so if you keep the temperature of the gas high enough so that you avoid fragmenting the gas into property stars, but rather keep a large amount of gas available to form only one single massive, very massive star, then you can form a much larger massive black hole seed. And similarly to what we see in the low redshift universe, we think that at high redshift, we can also have stellar compact clusters of lower mass stars. But if they're very compact, you can have runaway collision between those stars, just because the most massive one will sink first toward the center of your cluster. And we think that those can also form black hole seeds of 10 to 2, 10 to 3, 10 to 4 solar mass. So there are other scenarios, but I guess that's kind of put the picture, the broad picture of the field. And then of course we have many questions regarding those mechanisms. The property stars, they may be forming in many galaxies, but are they too light to actually sink toward the center of the galaxies and accrete efficiently? Massive seeds, sure, but are they actually too rare to explain that we have black holes in all galaxies in the local universe? Still ongoing research. So the channels of black hole formation determine the initial mass of the black hole, but also their location and their abundance. How many galaxies of the black holes? Do we have several black holes per galaxies? And we have to keep in mind that those channels are absolutely not mutually exclusive. So it could very well be theoretically a combination of all those models to explain observations. And what's very important for us is that the physics of those mechanisms is actually going from scales of very small clump of gas all the way to the large scale environment, for example, for the direct collapse mechanism. So how do we capture this in simulation, right? Where we miss mass and spatial resolution. So there have been three kind of approaches to do that. The first one is what I call observationally driven subgrid models for the seeding. So it's basically based on reproducing what we know about massive black holes in observation from the local universe or high redshift quasars. Some models are a bit more physical, so trying to form black holes at high redshift, for example, looking at the metallicity of the gas, because we want to form black holes in pristine or metal poor gas. And then there are models that are kind of mimicking one given specific model and trying to understand what would be the demographics of black holes formed through this model. And I guess this one are not tuned ideally. So I try to summarize the three types of models on timeline. Please do not be upset if your simulation is not in there. It was very hard to kind of read all those papers again, but from the bottom, it's going to be, and it's classified as the volume of the simulation. So at the bottom, you would have zoom in simulation and then small boxes, the typical 100 co-moving megaparsec simulation of the field, like illustrates, and very large volume in the field. Everything started kind of with isolated galaxy formation simulation, and then quickly the field kind of build a lot of different simulation from the big simulation of the field, but also smaller volume, zoom ins, and now again very large simulation. And I put also there the zoom in that we talked about during the last 2 days. So when we look at all those models, which do form black holes in the simulation, obviously the zoom ins that are interested in agent feedback, they do not really care about how you form the black holes, right? So for those, it's just you put a black hole as you want, kind of in the simulation. I forgot to say, very interesting, that some simulations do not form black holes, but they're actually super resolved and very interesting to actually see where you would form the black hole. So those were run early on, but they are still actually used in the field to understand black hole formation. So on all those models, all of those form black holes based on the idea that you want to reproduce observations. So for some of those models that were, simulation were carried out quite almost 10 years ago now, at the time, the observation that we had were not as many as now. So when we looked at the black hole stellar mass relation, and this is a compilation of different samples of observations, back then, what we had was actually massive black holes in massive galaxy when we think about the Cormier type, for example, relation. So simulation really wanted to reproduce this part here, So the seeding was made in a way that you would form a black hole in all the halos or galaxies in your simulation. And that was the big idea there. So there are different ways you can do that. Most of the simulation just employ an halo mass threshold, right? So every time you have a halo that is resolved, reaching a given mass, then you form a black hole in the center. So use on the fly, friend of friend on the dark matter particle. And then the most bound or the particle at the peak in the density field is basically converting into a black hole. Some simulation like SIMBA instead use the stellar mass of the galaxies, but it's the same idea that you want all galaxies to have a black hole. So the threshold here is a stellar mass of 10 to 9.5, and it's the same thing. You run a friend of friend on the stellar particles. A new simulation, recent simulation, Astrid, is using both criteria. So the most important one, I think, is the halo mass, but at least the stellar mass is ensuring that you would actually form the black hole in a system that is evolving already. You can already call it a galaxy and it's forming stars, basically. Okay, and then some simulations, still with the same idea of having one black hole per galaxy, actually rely on the gas properties. So this case for Horizon Agent and similar simulations such as the New Horizon or Obelisk that are all using the same Ramses code. So the idea here, so those code, like the Ramses is an adaptive mesh refinement. So you have cells for the gas. The idea is to form, to look over the cells and to form black holes in cells that reach the threshold, the density threshold for forming stars, basically, because you want to form where you form stars. And then you have other criteria to ensure that there is only one black hole per galaxy, so it's a bit cheaper than running even a friend of friend in terms of computational cost. So this is a visualization from Ricardo Beckman from the New Horizon. So you can see the galaxies and the black hole. And what's interesting with this exclusion radius is that in principle, if you form a black hole here, if your gas cell is eligible to form a black hole over there, because you're close to another black hole, you would actually not form a black hole there. So there is a bit of stochasticity in the formation of black holes. And then because you're not actually tightening the location of the black holes at the, in the center, for example, of the halo of the galaxy, you can actually form black holes, at the edge of some galaxies. So you can have ongoing black holes or black holes that could be wandering around in galaxies. So it's not so much visible in this figure, but if you look at the black hole stellar mass relation, those are observation, and those are the black hole in the simulation, you can think that, those black holes here maybe are actually formed quite far from the galactic center, and they will just not reach maybe the galactic center. Okay, so those were for most of the simulation of the field, and then you have the simulation that try to do something a bit more physical that we're interested in the seeding. So they do not make any assumption of how many black holes you should have per galaxy, or if you should have at all a black hole in galaxies. So they're also based on gas properties, and they're looking at parameters such as the metallicity, because you want to form black holes in metal-free, metal-poor environments. So what they look at is the density. So density of the gas has to be higher than the threshold for star formation, potentially in some simulation quite, much higher than what you would use for the star formation. They look at the metallicity, so either pristine gas or metallicity below a given threshold, sometimes temperature, and for the direct collapse, what is important is to look at the intensity of the Lyman-Werner photodissociating radiation, or H2 fraction, because you want to keep a large amount of gas available to form only one single massive star that would collapse into a massive black hole, right? So you need to keep the temperature of the gas high enough and then avoid H2, that is an efficient coolant at high redshift. So to do that, you can either look at individual gas particles, for example, in SPH code, or you can look at what we did in Ramses. We first run so the approach is not based on single particles, but it's based on clump of gas that are a bit larger. So what we do, for example, is to run on the fly a clump finder. So identify a lot of clumps everywhere in the simulation. And for each of this clump, we verify some of those criteria to make sure that that lamp is eligible to form a black hole. So it's more expensive, probably more expensive than some of the other methods. And then some of those grid models actually rely on the probability to transform a gas particles or a clamp into a black hole. So not all of them that actually are eligible would eventually form a black hole. And this probability can be a few parameters. This was used in Gillian Delovary, where she was taking different parameters to see the impact on different quantities. And then in my case, it was based on the POP3 IMF, so a bit more theoretical in a way, although we do not actually have POP3 stars in the simulation. So the result of that is that, how am I doing for the time? Okay. So the advantage of using this kind of more physically motivated approach is that the seeding is happening more at higher redshift, as we would theoretically expect. So from Julian's work here, you see that all the seeds are forming relatively early on in the simulation, and by the end of the simulation at redshift 5, you only form a few seeds. This was also shown in this figure for Michael, where if you're using those criteria, you're forming black holes early on, and then it stopped because of the metal enrichment. But if you're using the halo mass threshold that is used in most of the large-scale cosmological simulation, then you keep forming black holes all the way down to the late universe. Okay, so then how do we actually constrain this with observation, right? Because there are not that many constraints on black hole formations. So what I think that we can look at, if we employ a physical, some good physics model, is to look at the occupation fraction. So how many galaxies actually have a black hole? And this comes as a true prediction from your simulation. So in Julian's work, it was nice to show that the occupation fraction is increasing as you're building more and more massive halos, just because as a result of the hierarchical building of the halos or galaxies. What's interesting is that not all dwarf galaxies would actually have a black hole. So you can test that if you're, having a lot of observation of black holes in dwarf galaxy or not, which is also challenging. And then as you go to more and more physical seeding, what you need to take care of is the older physical processes that are becoming very important. So for example, here we tested different implementation of supernova feedback. And since metallicity is a key ingredient of the model, the way you do supernova feedback will actually change the probability for a galaxy to have a black hole. So, metal dispersion feedback from supernovae agent, the environment is also playing a strong role. In reality, what we constrain is actually not the black hole occupation fraction, but it's the agent occupation fraction. So although you can take all the big simulations that form a black hole in all halos, all galaxies, so black hole occupation of unity, when you move to the agent fraction, and this is what is shown here for different luminosity of the agent, then first you get different results. And then when you compare to observational constraint, it's not always matching very well. So a lot of physics is actually getting into, going from the black hole occupation fraction to the agent occupation fraction. And, in simulation, we have too many agents in those dwarf galaxies. So, are we seeding too massive black holes? Is the supernovae or agent feedback too inefficient in those galaxies? Should we move to use something that is different from the Bondi accretion model that can boost the accretion if you have a massive seed? So yeah, challenging field. I think we will hear more later on today. So very quickly now, what does it actually take to look at direct collapse black hole in cosmological simulation, right? So this model is particularly challenging. So if you go from a big simulation, like this is just post-processing TNG50, so all the stars are where I would think that direct collapse black holes could form, just based on the intensity of the Lyman-Werner radiation that is needed to suppress molecular hydrogen. So basically, those direct collapse black holes would form where you have star-forming galaxies nearby that are providing you this photodissociating radiation, but you have to be far enough that you do not get polluted by the metals. So it's a challenging, balance between those aspects. But what you really need to do when you have those candidates is to actually run zoom in simulation to actually see if your clump or where you identify your direct collapse candidates can actually form a direct collapse. So this was done in those papers where really you zoom in and you see that the direct collapse is in this pocket of pristine gas while being close to a star-forming galaxy that is here. So this was, I'm going very fast on that, we'll hear more about it, but this was also studied in the Renaissance simulation where you have the direct collapse candidate here, and this is, I think, the metallicity. So you have to be close enough, but also far enough that you do not get polluted. And then again, you have to zoom in quite substantially to really verify whether you would form or not a direct collapse black hole. So this, I think you will talk about that, but it was nice to see that, the Lyman-Werner radiation is maybe not, doesn't need to be as strong as what we initially thought, so more optimistic view. And the other scenario that, how do we, it's more like a question, but how do we actually model this in larger scale simulation, such as Illustris? And then very quickly, once we have the location of the seeds, we want to use an initial mass for the seeds. So there have been different approaches to do that. Either you just choose whatever you want to reproduce observation. This is done in, Illustris CNG. You can draw the initial mass from a power law distribution. This has been done in Astrid. It's really improving the stochasticity or the scatter in the black hole stellar mass relation. If you're using something more physical, you can tight your initial mass to, mimic more like a light seed or a heavy seed. And in my case, I was using the local gas properties and the POP3 IMF. It's literally, I have 2 more slides, but they go very fast. I just to show, what we get, like how the seeding models in simulation reproducing observation. So this is a local universe, black hole stellar mass relation. The simulations are in green, and we're comparing with observation in the local universe. So you can see that if you're employing a very high seeding mass, you're not reproducing the low mass black holes in dwarf galaxies. And then this was the Astrid. We will hear more about it. That is, if you have this distribution of initial mass, you increase the scatter here. That may be more similar to observation. And just a teaser, because I really kind of want to discuss with you at some point the James Webb discoveries. Very excited about that. So I put a compilation of all the simulation at high redshift this time. We're looking at redshift 6. The control plot is high redshift quasars. Agent detection are in red in this black hole stellar mass relation, and then the simulation are in blue to green. So, I'm happy to see what is your takeaway about the agreement between simulation and recent detection. I still think that, we are kind of okay, but I'm happy to learn about overmassive black holes, what we should get from that. Thank you.
Are there any questions for Melanie?
Hi, thanks, Melanie. Great talk. So when you use, say, a temperature criterion that many simulations use to model, say, direct collapse black holes using a minimum temperature criterion, I know that like many simulations use this equation of state prescription for modeling the interstellar medium, which very often has a temperature floor of 10 to the power 4 Kelvin or so. Do you think that can impact negatively the way we model seed formation?
Yeah, I'm not using a temperature criteria, so I guess you will have to ask Michael, other Romanus people. Yeah, I mean, how much you can resolve, how much you can I don't know exactly how, this is also resolution dependent probably. Yeah, I haven't done it myself, so I wouldn't be able to say. I haven't seen any figures where this is actually tested for the exact threshold. No.
Thank you.
Are there any other questions?
Yeah, thanks for the wonderful talk. So you had a plot that had the AGN occupation fraction. And so I'm curious in these plots if an AGN is defined as an AGN based off of some sort of like accretion rate and the simulation, and what are the prospects for comparing this to observations in galaxies, how they define an AGN versus with these simulations?
Yeah, here it's really just based on the accretion rate into the simulation. We are converting this to like bolometric luminosity, and I think here it's actually X-ray luminosity. Yeah, that's what people have been doing from most of the simulation and agent studies from there. I mean, you could model the SED, and then in specific, if you're interested in specific wavelength, we're doing that for some simulations, some studies, but yeah, then if you need to model this for all the agent in simulation, it can, if you want to really do the SED, you need to look at the metallicity of your galaxy. So, the particles in the galaxies, all the different parameters. So it's quite, can take some time, but yeah.
Any other questions?
Thanks. Just on your last slide there, it's in prep, so I hadn't seen it before. Yeah. So what is that telling us? Is it telling us just at even the bottom to like the blue tides in Astrid, is it telling us that if we have seeding there, we're seeding them too small or something, or they're not growing fast enough?
Yeah, I mean, my takeaway from that is that, okay, so to be fair, they're not including some of the most recent papers, so you have even more like detection here from the Myolinos paper.
Okay, yeah. That would be lower down though, at least.
My takeaway from that is that the error bar on the stellar mass is actually still, quite large. So like, right. So like if you take all the upper limit, then you're still consistent with like the scaling relation that we see in the local universe, right? But I'm interesting to know what observers say.
Yeah. The black holes are definitely larger, right, than what we're seeing, if I'm reading that correctly.
I mean, the error bar on the black hole mass probably is also important, right?
Yeah. So it could be worse.
So what's interesting actually in the Myolinos paper is that they are plotting this as a function of the stellar mass, but also the gas mass and the velocity dispersion. And only the stellar mass is producing these black holes that are off. But if you look at the gas, it's actually like very consistent with like what you would find for more massive galaxies, and the velocity dispersion is also consistent. So yeah, I'm interested to know I think it's still puzzling. Yeah.
Okay.
Just following up on what John just brought up. I'm very biased on this, but I think that there are strong observational biases as well. I mean, I'm not saying that observations are wrong, but just the selection criteria require these to be AGN dominated. And if you look at this statistically, this means that you will select over massive black holes. There is lower bias, it is well known, but on top of this, it's for the faint objects, you also need the AGN to be brighter than the galaxy. And this is a second bias on top of this. So, I mean, this is the most interesting thing that I've seen in the last, I don't know how many years, so I'm super excited. But I think that this is something that we have to take into account before saying, before drawing strong conclusions about seeding per se. But what I think, to me, what is really important is really how do we get to these masses? Even if these objects are super biased, we still need to grow them.
Yeah, so, exactly. They can be the outliers.
Exactly.
Right, but like we're still way off the outlier.
Exactly. So it's exactly the same question that we had for the quasars at Rashi 6-7. Now it's even, it's just higher redshift, smaller masses. Are we looking at 5, 7 signatures? I have no idea. But anyway, this is just amazing.
That's exciting, right?
Yeah. Any other questions? I just have one question, actually. Has anyone done this, or maybe it'll be talked about today, just comparing these super high resolution simulations, trying to predict really accurately where you'd form a seed? Has anyone compared that to like where the low resolution simulations are putting the seeds and seeing if that actually matches or not?
Yes,
I don't think they have actually, but I think that would be that's a really key point.
Because you know where they are, and the high, you can just go like do the same halo at low resolution.
Yeah,
see if they end up
exactly.
in the same place at the same time.
Exactly. Yeah, I think that would be a little bit about that.
Nice. Good. Okay. I guess that's it then. So let's thank Melanie again.
Thank you.
Think so, maybe tap it on the.
All right, so we're starting the first session. There will be 4 15-minute talks. Maybe I'll give you an 8-minute warning.
Okay.
And our first one is modeling supermassive black holes in cosmological context from their origin as black hole seeds down to the local universe. So nicely thematic. So Danielle, why don't you take it away?
Yep. Thank you. Okay. Okay. Not okay.
It'll come on in a second.
Okay. Yeah. Thank you. Thank you very much to the organizer for having me here. It's really a pleasure to be here. It's a very interesting meeting. I am Daniele Spinoso. I am a postdoc at the Tsinghua University in China, Beijing. And today I'm going to present this L Galaxy's black hole semi-analytic model, which has been an ongoing effort for some years now with the collaborators that I'm highlighting here. And yeah, you also hear something more about this model in the next talk from Marcos Polkas. So just to give you a bit of an overview of this model, this is a modified version of the Munich galaxy formation model known as L Galaxies, simply. And it's actually coming out from the 2015 version, which was presented by Bruno Enriquez in 2015. And it's a semi-analytic model, so it's a tool that models the baryonic counterparts of dark matter halos, which are extracted from merger trees of large volume and body simulations. So everything that I'm showing today has been developed on the Millennium suite. Wait. Okay. I don't know what happened. Yeah. Well, the color changed. This one. But we already started to test the same model on the Lustrous TNG suite, and yeah, it's actually converging. So this is very interesting. And well, the focus of this model is actually to describe the formation and evolution of massive black holes starting from seeding down to local universe, to the redshift 0. So let's see. Yeah, as just Melanie very nicely reviewed, we actually implement 4 different channels of black hole seeding, going from the low mass POP3 stars of the order of 10 to the 2 seed mass, all the way up to the massive heavy black holes forming via direct collapse. We also add to what Melanie described, this merger-induced channel, which is basically the formation of heavy seeds during gas-rich galaxy mergers at high redshift. And it's just an additional channel to have direct collapse in the end. And one issue we face is that the Millennium 2 simulation doesn't have enough resolution to model self-consistently the formation and evolution of POP3 stars, so light seeds in the end when the POP3 stars end their life. So what we did is actually to resort to the output of the Gamete GQD model presented in Valiant 2016 to inherit the evolved counterparts of light seeds and plug them, graft them in to our Millennium 2 halos as initial conditions for the black holes. On the other hand, intermediate mass, so black holes forming in dense stellar clusters, for instance, or heavy seeds, so that collapse, were actually followed self-consistently in this model because we were able to track the spatially varying UV background, so Lyman-Werner background, and the chemical enrichment of the AGN, as I'm showing here in these 2 plots for 2 black holes that form at redshift, let's say above somehow 10. So with this model, we actually have a way to track fully self-consistently the nurturing environment in a 3D box and in a cosmological context of these intermediate mass and direct collapse black hole seeds. This can be somehow scaled, although the resolution is a clear issue because we need to resolve either atomic cooling halos or mini halos. So we are working on that, and stay tuned. And regarding the results of this model, well, of course, I mentioned the merger-induced direct collapse black hole. The issue with these in the Millennium 2 is that the volume is actually small to have the condition for them to form efficiently, let's say. So we only have few halos, but the model is there and these objects can actually be predicted. So one important point of this model is that the formation of black hole seeds is actually connected to the physical properties of gas and so to the environmental properties. And so black holes only form until the conditions allow. And this black hole seeding epoch, let's say, ends at redshift 6. After that, black holes evolve self-consistently and without any more black hole forming down to low redshift. And this is actually interesting because the outcoming population of black hole seeding processes is consistent with local observations. As you can see here, I'm showing the black hole mass function. We get a redshift 0 and black hole to stellar mass relation, also at redshift 0. I'm not going to comment on this. If you want to speak about it, I'll be very happy, but now I really don't have time. So after they form, black holes grow their mass via different channels from hot and cold gas. And we track this self-consistently as well. Black holes basically accrete gas from the cold phase through sort of a two-phase model, which includes a first Eddington limited, very rapid accretion phase, and then a more quiescent phase where the accretion rate actually slowly declines in time. And while the black hole grows, we also follow the spin and couple the spin to the growth of black holes. So this is actually done on the fly, so, again, self-consistently as the black hole evolve. And these allow us to draw prediction for the black hole, for the QSO, the quasar luminosity function at different redshifts, as I'm showing here on the right. This was obtained on the Millennium simulation and the spin distribution, also at redshift close to 0, so 0.1 here on the left. And wait, sorry. Once black hole, well, after galaxy merger, black hole can merge themselves. And we model also the possibility that these black holes receive a gravitational induced kick. So they are ejected from the galaxy. And so we can produce a wandering black hole population. Also, this was modeled on the Millennium. One of the key outputs of this model is that wandering black holes do not grow. So this has an impact on the bulge to black hole scaling relations, for instance, as you can see here for pseudo bulges. And of course, we can predict also the distribution of wandering black holes as a function, for instance, of stellar mass of their host or reference halo. On top of this, there is also a new part which models the dynamics of black holes, also self-consistently and on the flight, which basically describe the formation of massive black hole binaries after galaxy merger, following the shrinking of this binary since their pairing phase at galactic distance scale, down to the hardening phase, sub-galactic scales, and all the way down to the gravitational waving spiral. So with this, we have a sort of a natural way of describing the delays between galaxy merger and black holes, and of course, the formation of binaries and their gravitational wave signals. And this was actually used to predict some future observation as the ones we are expecting from the LISA experiment. In this paper here on the left, Lopes actually focused on identifying the merger signature. So the observational signatures of LISA host events. And on the right here, this was a prediction for the gravitational background, the stochastic gravitational background obtained from PTA experiments. This code is part of the code comparison project for LISA. So there are a bunch of codes, a large number of codes that are building catalogs to draw prediction for the LISA experiment. One thing is we can also have directly from the code mock survey outputs, which are basically adaptable to any arbitrary photometric filter set. And these can be actually used to mock surveys, mock real observation in a very nice and consistent way. Okay, I'm gonna go very fast on this because I only have 2 minutes. One of the nicest application I think of this model is that they can be, since they are so flexible and fast, they can be used to actually test physical prescriptions on very large volume and in a consistent way. So here I'm showing an over-prediction of the luminancy function at the faint end, especially at high redshift, which is something that happens in simulations, as Melanie recently summarized. So it's a known issue, but here with this model, we can actually start to say something or explore why this happens. So what we did recently is to explore different prescriptions for how the gas actually reaches the black hole or how the black hole consumes their gas. I'm not going into detail here, but you can ask me, of course. And we are start to seeing some favoring towards, for instance, low accretion in low mass systems, or the need to account for the spin of black holes to slow or delay the growth at high redshift and recover the luminosity function of AGN at redshift 2, 3, and 4. Okay, this is all. This is my take-home message. So semi-analytic models, and in particular, when they are so comprehensive in terms of black hole physics, can be used to test prescriptions that we actually use in hydrodynamic simulations, for instance, but also the other way around is true. High resolution hydrodynamical simulation can actually inform the analytic recipes that we use in the semi-analytic models. And this is something that we talked about in this conference a lot in the past days. So I think it's really a crucial point of having these detailed and comprehensive models on a wide, larger volume. And that's it. In case you're interested about this model, please feel free to ask me about the upcoming Hell Galaxies meeting in Spain in January. That's all.
Questions?
Yeah.
Very impressive, thanks.
Yeah.
So, so in terms of the merger, the modeling of mergers, so what do you predict about the merging timescales of low mass seeds at high redshifts? Is it as bad as they show in the
that's a
simulations?
good point. We still don't have resolution enough to go to that because Millennium 2 doesn't really follow small enough halos, say. But we are working on very high resolution and body simulation to to tackle what happens at redshift higher than 6 in greater detail. So I cannot give you an answer now because I don't know, but it's something that is actually very interesting to check, and we will go there at some point, I hope. I cannot tell you a definite answer now, sorry.
Thank you.
You're in the
Really great work. So 2 quick questions. So first, you said that your model, the black holes in your model care about the gas properties, but like how local or global are you talking? Because I mean, is it like a halo level gas property, or does your SAM actually have more like resolution?
Yeah, I mean, it's difficult to speak about gas properties in terms of resolution because semi-analytic model actually don't have gas cells, for instance, so I can, right? But yeah, generally the model basically stops at the halo, let's say, and the baryonic content of the halo is modeled in 3 different steps. Let's say there is a hot phase, a cold phase, so you can imagine a cold gas disk and then a stellar component. So up to the halo dimension, we can say something until, I mean, that's, sorry, but that's the resolution limit that we have. So I would say, yeah, orders of kiloparsec, well, tens of kiloparsec at high redshift.
Okay,
No,
just
no
one
less than that.
quick
Yeah.
question too, where you said you create mock catalogs.
Mhm.
Is that all optical infrared, or do you also go to like X-ray radio? Like what sort of mocks are we talking?
Yeah, that's a good point. So now the code has only SEDs for galaxies and emission lines. We are adding, right, in this period, the AGN SEDs, and that would go, yeah, all the way from infrared to X-rays. So yeah, not yet there, but again, probably soon there, hopefully.
Yeah, last question.
Great talk. So just wondering if you have tracked how many black holes would have been seeded if you didn't stop at redshift 6?
No, I never did that just because I mean, I wouldn't be sure about how to do that in the sense that at some point the conditions for seeding are really not verified anymore. So I would like to know what you mean by if they had been, I mean, what do you?
There are some models that are continuously seeding
Oh, I see.
throughout time. So I wonder if, say, like the reason why you don't have like a million more black holes that were seeded between Russia 6 and 0 could be the result of the things that you were saying that.
Yeah, that's interesting. Well, again, the model can be run without the seeding tracking. So you can just put one black hole per halo. And yeah, that's a good point. Worth checking. Thank you.
Awesome. Take Danielle again. Right, so our next talk is do IMVHs grow by accreting stars?
Yeah.
That's
I don't think I entered the correct mode. I don't know.
You go into present again?
Yeah. Play from start, no?
Oh, yeah, go into present again.
Okay. Is it?
Yeah.
And then this?
Yeah.
Yeah, perfect. Hi, everyone. So I'm the scientific child of Daniele, working with Silvia Bonoli in the North International Physics Center in San Sebastian, Spain. And today I'm going to continue from what Daniele gave me like a great introduction to the model to find an application in actual answering this question, which I will only do in the last slide, but I will motivate everything till we get to there with observations from tidal disruption events. What is a tidal disruption event? Nobody has talked about it so far. So black holes can be disrupting stars, given that they are hosted in a really dense nuclear environment. And actually, all the stars that will enter a tidal radius will get destroyed apart. Well, here we assume that only full disruption takes place. So all the stars, we consider the stars that enter inside, but of course, you can destroy them when you pass closing away. And why this is important is because not all black holes can disrupt stars, but only the ones below a certain mass, which is called the mass, the Higgs mass, which the event horizon operation, around 10 to the 7, 10 to the 8 solar masses. And this is simply because the event horizon scales with the black hole mass, the tidal radius scales with 1/3 of the black hole mass. At some point, this radius is within the star for main sequence stars. Of course, you can still disrupt supermassive stars, like giants, not supermassive stars, around 10 to the 9. And these are events that we have actually observed. So this is what light curves would look like a brief introduction for those that don't know. We see a rise within 10 to 100 days, and then a decay with a characteristic time parallel. And actually, these are among the most bright transients that we're observing in the sky. And only recently we have complete samples in optical and soon in X-rays, and less than 1 month ago in some in radio. So why speak about TDs? This is seeding. Well, instead of going with James Webb at high redshift and constraining the physics of seeds, there are supposed to be some seeds left down to redshift 0, which have grown, they're really undergrown, let's say. And this is something that is promising to probe with tidal disruption events. So all the inactive small black holes in dwarf galaxies, they can make TDs. And if we detect the signal, we can infer their environment and many of their properties. But to do that, we need a realistic model with realistic rates, and also not only for the black hole, but also as I will talk about nuclear star clusters, for example. And once we have that and we make predictions, we can answer finally the question if black holes can grow through TDs, because we will have understood the phenomenon. So I will totally skip this slide. I will just stress that we're using the high resolution Millennium 2 box, which is 100 megaparsecs, and that the spin we get compared to Millennium 2 converts to a median value of 0.6 for massive enough black holes, because essentially they average out when they accrete from different directions. It's a really nice spin model that I will refer to later. So we have bulges, we have stars, we have this beautiful black hole mass function that is really compatible with observational constraints. and we have spin. Of course, below 10 to the 6, we are quite constrained, but still we can make predictions. What we need more is nuclear star clusters. And the way to implement this is, which is simply a phenomenological model. We just assign to each galaxy a nuclear star cluster according to a scaling relation for now that breaks at lower masses. We then have to assume a profile for the nuclear star clusters because this is important when computing the TD rates. And to do that, we assume that nuclear star clusters forming the centers of galaxies by the inspired of global clusters. There's these simulation profiles from Donini, 2013. And then you have to make an assumption of how many nuclear star clusters are there, actually. So there are these constraints of the occupation fraction. And as you can see, around 10 to the 9 to 10 to the 10, in different environments with different colors here, all galaxies, essentially 8% of the galaxies host nuclear star clusters from observations. And this is something that is captured by a model by assigning at all black holes a nuclear star cluster and then being shaped by the black hole occupation fraction itself. So this is something that we didn't expect it, and it came up from the model. If you assume that all black holes have a nuclear star cluster, you can actually reproduce the observable nuclear star cluster in the local volume. I would like to highlight. So okay, we have these assumptions for black holes environment. Now we need to compute the rates. And to do that, we use phase flow, which has the advantage of delivering time-dependent rates, solving the actual 1D Fokker-Planck equation. And as I say here, this is different than steady-state approximations that just assume for a given black hole mass, a given rate. We actually evolve a profile around the black hole for each black hole in our simulation, essentially. And I show you here the rates. You can see for bulges on top, these are pretty constant in time. But as you model nuclear star clusters, time matters. And for the lower black holes in the smaller reservoirs, rates drop with time. And this is something that have never been considered. Well, there have been considerations, but not in a cosmological context. So we create a grid of these environments, these runs, and we plug it in back in galaxies with some additional assumptions on when to reset this clock of counting the rates and the evolution of the profile, because you have mergers, disk instabilities and stuff. And without further ado, go to the results of what we achieved. So with blue, there are the latest constraints from ZTF, Zwicky Transient Factory facility, with 33 TDs detected only this year. And as you can see, the model, the red line, reproduces at the high masses as a function of black hole mass and as a function of stellar mass, fairly well the constraints. And actually, what's interesting is that in order to do that, it proved really important to have a nuclear star clusters. So if you consider only the rates coming from searchy profiles around bulges and this, you will not be able to reproduce that. So modeling these like concrete modes of stars in the center of galaxies is really important, at least for TDs. Another finding, because of the time-dependent rates, is that at the lower masses, our model predict self-consistently compared to these like simple approximations done before, that in dwarf galaxies, you expect less TDs than actually observed. And this has, well, there are many implications when constraining TDs. One of them is you can constrain the spin, because as I told you, at the event horizon suppression, black holes with spin will have smaller horizons, so they can disrupt at higher masses. So this is something that is done here. I show you from spin 0 to maximally spinning, and our model produces the shape, the actual correct shape from observations. This is for the high mass end. There's some other factors, of course, to be taken into account. I don't have time to go through them. But also at the lower masses, which we expect like remnant seeds to be detected, we see we have an incompatibility. And this is something I want to discuss because we predict a high amount of black holes at 10 to the 5, 10 to the 6 with our model. But as you can see here, on top, if you use like the really simple assumptions for scaling the rates, you predict a flat distribution of black holes. So having self-consistently modeling these events can actually consider the black hole mass function at the low mass end. And of course, may indicate what could be going wrong for the lower mass end of the predictions from other models. Well, one of the main findings, and before I go to the final result and I will stop, is that we predict a high black hole occupation fraction with a model and a high nuclear star cluster occupation to predict the TDE rates. So this is something important, and all our results converge to this direction. And now let's talk finally for the growth. As you can see, this is the fraction of the black hole mass content as a function of black hole mass at redshift 0 and redshift 1. And as you can see, black holes don't grow, of course, because of TDs. They grow mainly because of gas, which is with blue. But around 1%, they grow through TDs. And actually, it's more, they grow some significant amount of their black hole mass. So we're only now starting to taking this into account in last results. So yeah, I will just drop my results here, and thank you for your time.
Fun talk. Do we have some questions?
Yeah, I guess I'd like to better understand if you have a high occupation fraction of black holes and nuclear star clusters, what is it that's actually causing that flattening in the dwarf galaxy regime for the TDE rate? Is it something about the profile of the nuclear star cluster or something like that?
Meaning the observational constraints as a function of black hole mass.
Yes, but my takeaway was that your model can reproduce that qualitatively too. Is that correct?
Yes.
Yeah.
So the fact is that smaller black holes, because we don't use scalings from derived from high mass end, they're hosted quite frequently in small reservoirs galaxies. And with the scalings, we assign a small nuclear star cluster that, as a function of time, within 10 mega years, will deplete its rates. So we have a lot of relic small black holes that cannot actually have these high TD rates, that it's only at the initial phase of the relaxation of the profiles. I don't know if it was too complicated.
Can I ask a question? Do you worry about our lack of understanding of observationally of TDE rates and all this business about the color of the galaxy mattering? It's a big anxiety for me.
Well, I have we will work on that. Here, we are making some qualitative comparison as a factor of, you have color of galaxy and a stellar mass, and from observations, most TDs right in the green valley, right? We somewhat reproduce that, but these are not, this model, it's not having these high rates that they seem exceptional. These are basic rates that we're reproducing. But yes, it's something to take into account, this overrepresentation.
Are you saying that your model both reproduces observational rates and somehow is tied to the...
We are trying to find out. I believe it's not reproducing this Green Valley effect.
Okay.
Because we don't have that high rates to start with. So there works with AGN, with many other factors that can boost the rates, which are not included in this work.
All right. Last call. All right, let's thank Marcos again. Next speaker is Aklog Baumick. Hope I got that right. Black hole seeding and cosmological hydrodynamic simulations, a novel, flexible approach.
All right. Thank you everyone for the opportunity. So my name is Aklant and I'm a postdoc at University of Florida. And today I will be talking about this novel approach towards modeling black hole seeds in cosmological hydrodynamic simulations, particularly of the high redshift universe, which has the unique feature of being able to represent a given theoretical seeding scenario across a wide range of simulation resolutions. And in the process, be able to directly confront the fact that in most large volume simulations, we come nowhere close to resolving these seeds coming from these different theoretical seeding channels. And Melanie, of course, gave a really nice review of a wide range of seeding approaches that have been taken in the past, which allows me to skip the first two slides and move straight to the main body of my talk, which will be in two parts. In the first part, I'll talk about how we develop these new seeding prescriptions using high resolution Zoom simulations. And in the second part, I'll be talking about how we implement this in uniform volume cosmological simulations. So the basic idea behind this flexibility is the fact that we develop two distinct types of seed models to handle two distinct cases. In the first case, where we have a high enough resolution, we are able to fully resolve a target seed mass. We have a gas-based seed model, which I'll talk more about. And in the second case, where we cannot resolve the target seed mass, we develop this novel approach called the stochastic seed model. Let's start with the first case, where we are able to resolve the target seed mass. In this case, we have this gas-based seed model, which comprises of these two basic seeding criterion. The first criterion is the minimum mass of halos of gas that is simultaneously dense enough to form stars, but also devoid of metals. And we explore variety of these thresholds from 5 to 150 times the seed mass or so. And in the process, explore different possibilities of the seed formation efficiency in terms of how much star-forming metal pore gas mass can be effectively converted to a black hole seed for a given seeding channel. And then we also have a minimum halo mass criterion of between 1,000 to 10,000 times the seed mass, which ensures that the seeds are forming in the halos with deep enough gravitational potentials. And we also explore some additional Lyman monoflux criteria, gas spin criteria for direct collapse black holes, which I'm going to skip in the interest of time. So when we apply the seeding criteria in our Zoom simulations, we find that a vast majority of these seeds are forming in these metal pore pockets of gas in partially metal enriched halos that are already undergoing the process of metal enrichment, rapid metal enrichment. So here's an example of a seed formation site. You have the gas density, star formation rate, and the metallicity profile. And this yellow circle marks this region of dense metal pore gas where these seeds are forming. And you can see they're already engulfed by the significant amount of metal enriched gas. We also demonstrate that our seed models are very well resolution convergent. So here's one such seeding parameter where we show the number of new seeds formed at various redshifts for a target seed mass of 10 to the power 5 solar masses, simulated at 3 different gas mass resolutions from 10 to the power 5 solar mass in gas, all the way to the highest resolution we achieve of 10 to the power 3 solar masses. And we see that all these resolutions produce similar numbers of seeds, which is nice. And we also see this generic feature common across all of our seed parameters, which is this initial ramp up of seed formation due to onset of new star forming regions, followed by the eventual suppression and slowdown of seed formation because of metal enrichment. This also allows us to, what happened? Yeah. So this also allows us to perform this large systematic study of a wide range of seeding parameters while being agnostic about what set of theoretical seeding channels do our models actually represent. And we find qualitatively distinct signatures on the merger rates, particularly measurable by LISA. So for example, here I'm showing the merger rates of 10 to the power 4 solar mass seeds. And in the left, I'm showing 3 different dense metal pore gas mass threshold at the same halo mass threshold. And we find that seed model variations are somewhat stronger at relatively lower redshifts compared to much higher redshifts, which is in stark contrast with the case to the right, where we vary the halo mass threshold by keeping the fixed dense metal pore gas mass threshold. And in this case, we find that the seed model variations are much stronger at much higher redshifts. And this tells us that future comparisons between LISA measurements and a simulation prediction of one of these seed models will be a very useful probe for the seeding environments for these LISA binaries. Now let's come to the case which is most often encountered in cosmological volumes, where the seed mass, the target seed mass, is not directly resolved. In this case, we developed this novel stochastic seed model where the idea is to seed the smallest resolvable higher mass descendants of our target seeds, depending on the resolution of the simulation. And in the interest of time, I'm going to go through this rather quickly. The key point is, in order to faithfully represent these descendants, consistent with what the highest resolution simulations with the gas-based seed model predict, we need two major criterion. Actually, we need more, but primarily two. The first criterion is a redshift-dependent galaxy mass criterion, and the second criterion is the galaxy environment criterion, both of which calibrated against these highest resolution gas-based seed model simulations. Now, to build the galaxy mass criterion, what we do is trace the growth of these low mass seeds in these highest resolution simulations to the point where they assemble masses corresponding to the resolution of the low resolution volumes. And here I'm showing a case where we trace a target seed mass of 10 to the power 3 solar masses to the point where they assemble 10 to the power 4 solar mass descendants. And here is the galaxy mass at various redshifts where these descendants assemble. And we can see, first of all, there's a broad distribution of halos where they assemble. And that is precisely why we need a stochastic criterion to randomly draw the halo mass or the halo mass or galaxy mass where we see these descendants. And then we also have a distinct redshift dependence, which imprints onto itself the interplay of halo growth, star formation, and metal enrichment on seeding. For example, this transition in slope that you see in this relation is essentially marking the onset of metal enrichment, after which the seed formation is suppressed. And this, which is the output of our highest resolution gas-based seed model, becomes the input for our stochastic seed model onto our lower resolution simulations. However, we find that if we only apply a galaxy mass criterion, we substantially underestimate the small scale clustering of these higher mass descendants shown by this gray line compared to the gas-based seed model predictions shown by this orange dashed line. And that is precisely why we need a galaxy environment criterion, which ensures that we preferentially seed in these galaxies with rich environments shown over here. And then with this black line, you can see that once we add this criterion, we're able to appropriately model the small scale clustering. And from a physical standpoint, it basically means that we need to do this because at these high redshifts, these seeds are largely growing via mergers with very little contribution from accretion. And as a consequence, there's accelerated assembly of these descendants at these rich environments because they have a much more extensive history of galaxy mergers and subsequent merger-driven black hole growth. And it is only after we capture both the galaxy mass and as well as the galaxy environment criterion do we reproduce in our lower resolution simulation the results from the highest resolution simulations that resolve the target seed mass. And if we remove the galaxy environment criterion shown by this silver line over here, we substantially overestimate the black hole counts as well as the merger rates. So now that we have a stochastic seed model which is able to reproduce the highest resolution gas-based seed model simulations, it is time to implement these in uniform volume simulations. And this basically culminated in this creation of this new suite of cosmological simulations called the Brahma simulations, Brahma referring to the universe in Sanskrit. It's not a forced acronym, I couldn't find one. So the idea is to basically represent these low mass seeds in larger volume cosmological simulations without having to explicitly resolve them. The way we do that is by creating these three sets of boxes. And only in the smallest volume, highest resolution box, the Brahma 9 megaparsec box, do we explicitly resolve 10 to the power 3 solar mass seeds using the gas-based seed model. And then in the larger boxes, the Brahma 36 and Brahma 18 megaparsec box, we resolve the higher mass descendants. So 10 to the power 4 solar mass descendants in Brahma 18 and 10 to the power 5 solar mass descendants in Brahma 36, forming in these rich environments with multiple galaxy neighbors. And we are able to now self-consistently combine the power of all three of these boxes to probe an unprecedented range of black hole masses and luminosities at these high redshifts. So here I'm showing the black hole mass functions and AGN luminosity functions. And if we only probe the Brahma 9 box, then we are only able to probe black hole masses between 10 to the power 3 to 10 to the power 5 solar masses, and AGN luminosity is only barely up to the Lynx limit. But if we combine all three boxes, we are able to probe black hole masses up to 10 to the power 7 solar masses, and AGN luminosity is well past the Lynx and the axis limit close to the JWST limit at redshift 7. Here, I'm showing that we can do it in reasonably low computational cost to be able to probe multiple sets of seed parameters and do a systematic search, but I'll skip this slide in the interest of time. And here I'm showing the stellar mass versus black hole mass relations for one of the seed models. The different boxes corresponding to the same seed model are shown by these different colored circles. We compared against these JWST high redshift AGNs and also the local observational constraints. And we find that these simulations tend to predict overmassive black holes compared to the local scaling relations. And the most massive of these black holes tend to produce results consistent with these overmassive JWST AGNs. And this tells us that generally the community is excited about the possibility of heavy seeding origins to explain these overmassive AGNs. But our simulations show that it is not impossible to form these seeds even with lighter seeds, as long as they form abundantly enough, which they do in our simulations, and as long as they merge efficiently enough. And finally, I would like to demonstrate the power of this novel flexible approach where we are able to take a relatively low resolution simulation, which simulates only down to 10 to the power 5 solar masses, and still be able to distinguish between whether these black holes originated as descendants of light seeds or formed directly as heavy seeds. And here I'm showing the merger rates for a set of light seed versus heavy seed models. And we show that regardless of these individual variations, the heavy seeds tend to categorically produce much higher merger rates compared to the light seeds, particularly at redshifts greater than 12. And this tells us that even if we assume a very pessimistic scenario where if you say that at high redshifts, maybe LISA might not be able to localize black hole mergers below 10 to the power 5 solar masses, even then with the events that we do detect with LISA, we will still be able to constrain the light and heavy seeds. And with that, I conclude my talk. Thank you very much. Happy to take any questions.
We have time for a couple quick questions.
So you said that the initial black hole growth is driven mostly by black hole mergers. So how do you model the dynamics of the black holes? And are mergers important also for the light seeds? I think this is related also to your last slide.
Yeah, correct. So in our case, we use this very simple lame repositioning to model the mergers. So we are definitely overestimating likely the merger rates. But the idea is to basically keep all of the aspects of the galaxy formation model the same as, in this case, underlying TNG model, and to isolate the impact of just the seeding. And we are going to model more realistic dynamics for mergers in the next few papers.
One last quick question.
Hi, very nice talk. I have a question about the TNG model actually, because in your high resolution simulation, you are going down to 10 to the 3, 10 to the 4 solar masses, and the TNG model has not been built to work at those resolutions. I'm wondering what is the impact, in your opinion, on the seeding of these?
Yes, that is precisely the reason why we have a halo mass cut, to avoid seeding in halos that are significantly lower than the atomic cooling threshold. So we do not consider seeding in those halos at all, where we don't believe that the TNG model has enough physics to model the star formation.
Yeah, I was wondering more about also the thermodynamics of the gas, because such a small cell can have a thermodynamic evolution that is completely different because it's a small patch of the ISM, and the TNG model is very smooth in this respect. So I was wondering.
That is correct. And that's also another reason for why, instead of using the local gas properties, which we do not quite trust in TNG, we are using the halo average properties of the total star forming metal core gas mass. And in the next few papers, I also have a proposal written on this where we use more multi-phase ISM simulations to model seeds, where we do plan to use the local gas properties. Thank you.
Thank you very much. Hopefully we can continue these conversations over coffee. Let's have our last talk of the session. John Wise, massive black hole seeds and rapidly growing halos.
Okay, thanks to the organizers for giving me that opportunity to talk here about massive black hole seeds and their rapidly growing halos. This is some work done by, I want to highlight, two of my students, undergraduate Elizabeth Monet and Brandon Priest. He just started in my group, and I highlight two people that are here at this conference, John Reagan, who you'll be hearing about after lunch, and Brian O'Shea, who's remote. Okay, since I don't really have to go into much detail about the overview of the different seeds, but I'm going to be focusing on massive black hole seeds. So these are thought to be some of the most massive stars that are forming, but they're completely hypothetical. You know, it's bizarre to actually think of a star that's over 1,000 or 10,000 or 100,000 solar masses, but these types of stars can give us these massive seeds in the early universe. And what I was showing here in this movie is some very early work from now 15 years ago showing the direct collapse. It is a kind of a proof of concept of how can you actually have a monolithic collapse in a giant molecular cloud that's metal-free in the early universe. But there, at that point, we didn't see any fragmentation. We don't have any fragmentation of these massive clouds, these metal-free clouds. You would expect a supermassive star to form, but if you do start to fragment, you would get one of these nuclear star clusters or some typical galaxy. But to actually have one of these massive seeds to form, we need very special conditions for their formation in their high redshift universe. So the number one condition is, right, you have to avoid fragmentation. Otherwise, you're just going to form a stellar cluster. To do that, right, you need a high Jeans mass of around 10 to the 5. You need a warm I was about to call it ISM, but we have no stars at this time. So you need to suppress cooling, right, for metals and molecular cooling. And also, you need to have super high accretion rates. These are orders of magnitude higher than what you'd find in the present day, roughly above, say, 400ths of a solar mass per year, but this is work shown that was first shown by Jose Carlos-san. So here, this is low accretion rate. So this is the stellar radius versus the stellar mass. So here's the protostar on the Hayashi track, and then it contracts onto the main sequence. But once you go above this accretion rate, right, it's always bloated. It's being smothered by this massive inflow onto the stellar surface, and it remains kind of like a puffy red supergiant, emitting very few UV photons, and thus it can actually continue to grow to very high masses. Okay, so I'm not going to talk about this scenario much, but this is highly explored in the close pair scenario. Basically, Melanie touched upon this and talked about this, is that, right, you need metal-free or metal-poor gas, meaning that you need to be far away from galaxies, and you need to have the molecular poor because you can't cool. So you need to be close to these radiation sources. But this sets up a Goldilocks scenario where you have to be in this kind of annulus or shell. It's close enough to the galaxies, but not too close. So just the right distance away from a young massive galaxy. But what I want to show you about is a new scenario now 4 years ago that we found in a Renaissance simulation. So when we set this up now 10 years ago, we didn't include black holes, mostly because it was too hard, and because I wanted to include the feedback and X-ray feedback, UV feedback, radiation feedback. I was like, we're just going to focus on the first stars and the first galaxy of the universe. Primarily, the stellar components were the most interesting at that time. So this is a 40 megaparsec box. These are a series of 3 zoom-ins. Rare peak that's surrounding the most massive halo. Normal region, it's just normal overdensity in a void. So we can resolve halos down to 1 million solar masses, and we have a maximum resolution in this AMR simulation run with ENSO of around 20 co-moving parsecs. So between 1 and 2 proper parsecs at the scale, we include metal-free star formation, modeling individual metal-free stars, and that transitions to metal-enriched star formation. We include radiative transfer on the fly, and in each region we follow around 10,000 Mach 3 stars and around 1,000 galaxies. So at the time, it was a very large simulation. It's still difficult to deal with these data, but nowadays it's not that big. But it took 10 million core hours to actually per run, 9 months of real time, 30 terabytes per run. So just to give you a general overview of what was happening in the rare peak. So what you're seeing here is all of this population 3 star formation. In green, you're seeing the metals being produced. In white, that's UV radiation. And in orange, that's the heated and ionized hydrogen. So you can see these cosmic fireworks are going off because you have these population 3 stars that are being born, they're massive, they're living for 10 million years, and now we're static in time, kind of flying through this region here, just showing the different components within the simulation. This was all made with YT. This was amazing, not by me, but by graphics professionals, but at NCSA. But there are all the metals, but I want to point out that, if you have a galaxy forming, but if it did host a population 3 stars, most likely to be pre-enriched by those supernova. And now we're zooming into the most massive galaxy that has around 30 million solar masses and stars in a halo mass of 2 billion solar masses. But what we did find when we took this, we didn't include any black hole formation here, but we were curious about where could you actually find these massive black hole seeds actually forming, searching for metal-free and stellar-free atomic cooling halos. Now, we didn't find anything in the center here, but on the outskirts. That was very surprising to us at the time. But we did that search at the final redshift, redshift 15. We had 670 atomic cooling halos in the box in the zoom-in region. And we found 10 of these. We found 10 metal-free and starless halos that were atomic cooling, and at first, John Reagan and I were talking about this at a meeting, probably 2016, 2017. But we just thought it would have high Lyman-Warner flux, right? That was the standard scenario at the time. But when we started looking into this, it had typical J21. So it's 1 to 3. That's not very high at all. That's very typical. But when we started digging into the data more, we saw that these are rapidly growing. So basically, they're skipping over this population 3 phase here, where this is the minimum mass giving a Lyman-Warner flux, and this is the atomic cooling halo limit here. So if it's rapidly growing, right, you can have mergers, it can be disrupted, and if you have a merger, and then it takes roughly a sound crossing time to kind of equilibrate, and then to collapse, it takes another free fall time. But if it grows past this little gap here within some of those 2 timescales, you can actually forego typical population 3 star formation and start to have enough gas in the center of the halo to actually support this massive black hole seeds. So Melanie showed this gratefully to me. I was thankful for that we found these halos are not near to these young galaxies, around 10 to 25 kiloparsecs away. They have moderate radiation backgrounds around 3 of J21, and it's not a close pair scenario. But this rapid growth, basically, right, this promotes some sort of heating, because if you grow a halos, you're going to get some sort of heating from just the viral heating of the gas, because H2 cooling is very weak. It's very inefficient, and it doesn't take much heating to overcome that. But here's the halo, one of the halos that we studied in this initial paper, and is atomic cooling halo, so it's heated to 10 to the 4 Kelvin around it, but it becomes self-shielding to it, and it starts to cool and collapse into a disk here. And this disk is tumorally unstable, and it fragments into three clumps with roughly 10 to the 4 solar masses of gas. And they are rapidly accreting, and they would actually, the infall times is roughly around a million years. So just to show you the structure, it's cooled down to around 10 or 1,000 Kelvin, and it's turbulent within that. And it's kind of a mix in between this nuclear stellar cluster and a direct collapse, right? You would have roughly a handful of these massive stars. So I'm running out of time, but John Reagan went ahead the year afterwards to resimulate this with sync particles, and what he found was, like, this is the halo that he resimulated. Has 10 to the 8 solar masses on halos, but the most massive star was roughly 6,000 solar masses. And just for comparison, we looked at a typical mini halo, and you get the typical population 3 masses. But to look at the just the mass functions of these, in the halo, in this rapidly growing halo, you get typically around 1,000 solar masses of stars. And around, we have few dozens of these massive stars compared to the more typical population 3 stars at a time. But this is the new work that I ran out of time to show. But the question is, can we build a classification model to actually identify these direct class black holes? Because we have around 100 candidates in a population of 10 to the 5 halos. So we inspected these large scale quantities like the tidal field that Tiziana has looked at before, overdensity, distance to closest halo mass, spin, Lyman-Werner flux, the growth rate, and local properties as well. And in orange here, these are these candidate halos versus all the other halos that have in between a barrel temperature of 3,000 to 30,000 Kelvin. So we have these 12 quantities here, here, and here. I don't have time. I actually just saw these for the first time last week. And also, so Brandon. Yes. I'm going very good. But here, right, this is this, so we use a support vector machine to actually try to classify this very unbalanced sample. You can use a weighted classifier. And I mean, students have gotten pretty good results. This is still preliminary, so an F1 score of 83%, recall of 73%, and precision of 97%. So here's like, we have 107 that we get from a good classification, and 3 that are that are missed, and here are false positives of 12. So we've done some feature importance. The most one, I mean, the Lyman-Werner intensity, that a radial mass flux at a distance of 50 parsecs. Halo spin, that's interesting. I've yet to kind of digest this information, but I want to show these data. Very quick. I don't think this will be talked about today. This is not my own work, but this is about a streaming velocity, so you can actually suppress population 3 star formation. And I think these are great candidates for very, very high redshift seed formation, like redshifts of 30 or so, where you have a superposition of a strong streaming velocity. So this is 400 megaparsecs on the side, but if you have a very high sigma peak in that region, streaming velocities, you can actually suppress population 3 stars and perhaps get a massive black hole seed at redshift 30 that then gives you enough time to actually explain this redshift 6 quasars. So I'm completely out of time. I'll put up my summary here, and I'll take any questions.
Couple quick questions. Tony in the back.
Hi, well, a lot of information. Great. So I am still thinking about these massive seeds, which are 10 to the 4, 10 to the 6, at a halo of 10 to the 5. This is like you showed, or did
10 to the 8 solar masses for the halo.
Say it again.
10 to the 8 solar masses for the halo.
10 to the 8, right?
Yep.
Okay. It's still kind of like interesting to parse that it's like half the mass of the halo is the.
So what we're finding is like, maybe 10 to the 6, like that's even more gas than we have in the very center few parsecs of the halo. It's more like 10 to the 4 is the amount of gas that you have, but the amount of gas that is actually fragmenting is around 10 to the few times 10 to the 4. Yeah, so that's just under 1,000th of the total mass.
Can you go back to the new
Yes.
slide?
Thanks. Thanks.
I just want to keep you talking for a while. So
Yeah. You can take pictures. This will probably change.
No, but this is really amazing. I mean, we have been focusing on very few points, but I'm pretty interested in the spin because the early direct collapse models were were based on halo spin.
Yeah.
Then we thought that it didn't make sense.
Right.
But now perhaps it actually does.
I don't know yet, but it's slightly shifted, right?
Yes.
Yeah.
Well, okay. I will wait for the paper, but this is
Yeah. Since I've yet to, like, I saw a spin on the top 6. I was like, that's very interesting. We have to look at that a little bit more. And also like the tidal field, because these aren't the, like the seeds of Redshift 6 quasars. They're not going to be in like regions that have little tidal field. So, right. So they're on the outskirts. So more typical.
Right.
There's a question. Oh.
Last question, I think.
Really interesting stuff. I was wondering, like, when you're forming these black holes, you said 10 to 25 kiloparsecs or so away from the central galaxy. By what time would they fall into the central galaxy?
I think in this case, it's around Redshift 8.
Right. Okay.
Yeah. I did not have time to show that. I mean, let's see. I actually had these slides in here. Yeah. This is, it's already been published by Matthew Scoggins. But here, you follow the dark matter only simulations here. And here's a halo mass. So they're incorporated into larger halo around Redshift 8. And that halos are 10 to the 7. But then again, then it has to spiral in and grow. It's like, these aren't the ones that are, like, if I were just to look at the halos, they're not going to grow that much here.
Thank you.
You're welcome. Because I think these are the halos that were like producing those metal-rich environments.
So I think we could fit in one more question. Do we have someone?
So you showed a halo that had 3 DCBHs, I think. Is that a typical situation? And if so, should we be worried about them merging and then recoiling out of the halo?
So we found more than that. So that was only the hydro, but when we follow these with sync particles and like with accretion, we found even more of those. But that is super interesting. I'm pretty excited about the aspect of binaries or mergers happening and things that are being kicked out of the system. If this can actually be observed with, I don't know, this is intermediate mass, so either LISA or Cosmic Explorer, Einstein Telescope. So super interesting.
Thanks.
It's much more interesting to have a cluster of these than 2 or 3 or 1.
All right. Let's thank John and all the speakers from this session again.